So now it's time to talk a little bit about Bode plots, what they are and how to use them. What I'm going to do is first tell you the idea behind making a Bode plot, but we're not going to sketch anything by hand. I'm going to show you a lot of MATLAB, and we're going to talk about how we might interpret a Bode plot that we're going to see. So how do you make one? Well, first of all, we're going to think about a rational transfer function in the S domain. So I've used it in basically as general as I possibly can. We have some nth order polynomial on top and an nth order on the bottom. As an example, we might have this one here, which is a second order on the bottom and a 0th order. So beta naught is 10, and there's nothing else before it, just a random transfer function. We'll actually be looking at this particular one here, the bottom one, when we start doing Bode plots in MATLAB. So the first thing you need to do if you're actually going to plot a Bode plot by hand is to move it into the purely frequency domain. So if you remember from class, S is some sigma plus j omega, and it's a variable that encodes both frequency and damping information. It'd be nice to say sigma is just some damping ratio, but it isn't. It relates to the frequency and a bunch of other things, so it isn't just equivalent to the damping ratio. The problem is that in terms of frequency responses, we don't really care if there's any damping. For instance, if there's a resonant frequency, then it doesn't matter that it's damped resonant frequency or a natural resonant frequency. So instead what we do is we let S equal to j omega. So we only look at stuff on the imaginary axis. And omega is the frequency of interest. Now strangely enough, what we end up with is a function of just frequency. There's no more damping information, but again, we don't really care too much about that when we're looking at a frequency response. It certainly matters when we're doing, for example, a time domain response. Does the oscillation die off, for example? Does it even happen? Perhaps they're overdamped. All of that is important information, but the Bode plot does not concern itself with those sorts of questions. It's only looking at what happens if an input is, say, a sine wave. Now this function, no matter what, is a complex variable, and it is a function of both magnitude and phase. The Bode plot says the magnitude and phase are really what matter. So let's now take a look at how we're going to, first of all, use MATLAB to create a Bode plot, and then how we're going to interpret it. So I have MATLAB open here, and the first thing I'm going to do is produce a Bode plot of just a first order transfer function with no zeros. So I'll show you how I might do that. I'll say, my system number 1 is TF, and it has 1 on top, and let's say 2, 1 on the bottom. Okay, so this is just a continuous time transfer function. I can look at its step response by typing step, system 1, and MATLAB will compute the step response, and I'm going to just move it over to my other screen, and that's what that will look like. So it's a step response. You'll notice it doesn't oscillate, and what you might also notice is that although the step would be, for example, from 0 immediately up to 1, so very, very fast, essentially what that means is very high frequency, the step response is a little bit lagged. So it doesn't immediately shoot up to 1, it takes its time to get there. The Bode plot is going to reveal that that actually is not surprising, and so let's take a look at its Bode plot. To get a Bode plot in MATLAB, I just type in Bode and system 1. So now I'm going to bring it over and let's talk about the critical features of a Bode plot in MATLAB. So I have two plots, one for magnitude and one for phase. A complex number has both of these things, but unfortunately showing it in a single plot is too difficult. It would be something like a surface, so we're not going to do that. We're instead looking at two different plots stacked on top of each other. And every Bode plot you see in textbooks or in literature or now in MATLAB will be basically this. You'll have the magnitude at the top and the phase in the bottom. One thing to notice is that the magnitude is in decibels. So this is 20 log base 10 of the actual magnitude itself. Why that is the case is sort of historical. So when Bode was working on these things, he realized that if he wants to, for example, work out multiplication of two transfer functions, that's typically quite challenging, especially if they're rational functions. When you take the logarithm of these things, then you can end up with addition, because multiplication becomes addition. That sort of little historical note is not super important, because once people learned about how to make Bode plots, people started to realize they were useful for many different things and for much the interpretation that we can have. The phase, a little bit frustratingly, is in degrees, not in radians per second, radians. And if you look at everything else, so omega, for example, is a frequency in radians per second. And so you would hope, for instance, that maybe the phase would also be in radians, but that is not the case. And so what you're going to have to do is just convert a little bit in your head, but for the most part, we also really don't care too much about the exact numbers of the phase. We only look at a couple of very important things, for example, the phase margin and crossover frequencies. So for the most part, the actual numbers of the phase don't really matter too much unless you have a very specific input, and we'll talk about that in a moment. So let's now look at what this Bode diagram is telling us. We're going to ignore the phase for a second, and we're going to look specifically at the magnitude plot. So the first thing we notice is at 0 frequency here, which is this very, very leftmost edge, my magnitude is 0 dB. Now, if you remember, this is a logarithmic plot, so log producing a 0 means the actual magnitude is 1. And this is a very, very important frequency, 0 radians per second. It is our DC frequency. So if I give it a step response, for example, eventually after a bunch of transients die off, we're going to be in that 0 frequency mode. It's a constant is what 0 frequency really means. And the magnitude here essentially tells us where we settle. So what that means is as the step response dies off and all the magnitude or the transients are gone, that sort of thing, then eventually we're going to settle at a particular value. That value can be read directly from the Bode plot. So this is the value is 0 dB, which again corresponds to a magnitude of 1. And just to show you, I will put the step response as well. So I'll go back to MATLAB. I'll make a new figure. And I will, MATLAB is gone. I will do my apologies, I want a whole new figure. And I will step system 1. And what you'll see in the step response is that my magnitude, so finally it starts at 0 and I step it up and it goes up here to the magnitude of 1 in this particular case. So a step of 1 produces a magnitude of 1, and that's going to tell me essentially where I settle for a unit step, and the Bode plot told me that directly. Okay, I'm going to keep this, but I want to go and see that Bode plot again. And what you'll see also is this trailing off here. So there's a couple of important things you might look at. One is called the 3 dB frequency, so that's going to be somewhere around here. And when you're doing this in a real Bode plot, you might look at it more precisely. In MATLAB, at least modern MATLAB, you can click anywhere on the Bode plot, and you will end up with a tooltip, and you can drag it. So if I drag it and I'm looking for the 3, give or take over there, the 3 dB frequency appears to be at 1/2 radians per second. Why do we care about the 3 dB frequency? It's a little bit strange. It turns out that when you do the calculation, 3 dBs is when the magnitude is halved. So negative 3 dB frequency is if I were to put in a sine wave of 1/2 of a hertz, whose magnitude is 1, then I would end up with a sine wave at 1/2 of a hertz. The frequency, radians per second, the frequency would not change, but the magnitude would be halved. And different systems have different cutoff frequencies like that. And then we'll see also that this Bode plot is going downwards in magnitude as frequency increases. So what that means is essentially as we have higher frequency inputs, they're attenuated more than lower frequency inputs. And we saw that in the sine wave, or I beg your pardon, the step response. When we looked here, this step response would be instantaneously going from 0 to 1, so it would have extremely high frequencies due to that instantaneous motion, but the step response of our system is much slower and more lagged. Those essentially infinite and very high frequencies were attenuated, and now this is what a step response looks like when you attenuate those frequencies. It's essentially slower. And hopefully that makes sense to you. If the low frequencies are not attenuated and low frequencies are slower, and the high frequencies are attenuated and high frequencies are faster, then I would expect a slower response than the input. Okay, but how do we interpret these things? So we have our Bode plot, and it's showing us this magnitude and phase against frequency. Well, this actually is exactly what it sounds like. So if I put in a sine wave of a particular frequency as my input, then I expect its magnitude to be attenuated and the phase to be changed. Let's take a look. So I'm going to go back and find my negative 3 dB frequency, which again was about 0.5 rad per second. And there we are, give or take over here, 0.5 radians per second. I'm going to do the same thing on my phase, and I want to take a look. So when there we are, when my frequency is 0.5 rad per second, give or take my phase is negative 45 degrees. What I'm going to do now is give my system an actual sine wave input. I'm going to be using LSIM for that, so you can watch how I do that. and we're going to look at the input versus the output sine waves. What you're going to notice is that the frequencies do not change. The magnitude of the output sine wave will change, and because that negative 3 dB frequency, that's going to be 1/2 the magnitude. We're going to see the 1/2 magnitude. And the phase in degrees will be 45. So let's take a look at that. Okay, so I still have my system 1 here. I haven't changed that. I'm going to clear my screen. And to use LSIM, what's called linear simulation, I need an input, a time, and a system. The first thing I'm going to do is create my time. So I'm going to say T is linearly spaced points from 0 to 10 in 1,000 steps. U is sine of now 0.5 radians per second times t. And I want to LSIM the system, U, and t. System 1, I'm sorry. And this is how you run the LSIM. So this says that U of t is equal to what I've produced here, my sine of half a radian per second, and it needs a time to simulate, and then my system 1 is the system it is simulating. So if I hit enter, it's going to actually run that simulation for me, and it has produced a graph. And here it is. This is figure number 2 here. And so this is linear simulation results. And let's take a look at a couple of important things. So this here, the gray sine wave, is my input. And you'll notice it goes all the way up to 1 and down to 1. But if we look at my blue sine wave, which is the output, if we look at the magnitude there, the amplitude is approximately half. Okay, so once again, I sort of got that off of my Bode diagram. I had to get the frequency approximately. So my amplitude being half is pretty close to what I would expect. And you'll also notice that the phase is approximately 45 degrees. Now, that's a little bit more difficult to figure out, so I'm just going to do this qualitatively, but basically notice how the blue sine wave reaches a peak approximately 1/2 way down between this one's peak here and the 0, which is approximately 45 degrees worth of phase. So the Bode diagram tells us directly what happens to an input sine wave, to its magnitude and its phase. Now, the Bode diagram actually tells us quite a bit more than that. What we're going to do now is go back to that original transfer function I talked about in the presentation, and let's take a look at what its Bode diagram will do. So the first thing I'm going to do is make it, so system number 2, and that's going to equal to the transfer function. It was 10, 1, 0.1, and 10. So that was my transfer function there from the original presentation. And I want to show you if I give this thing a step response. So step system number 2. And what we're going to end up with, moving the diagram over, oh, my apologies, let us try that again. So step system 2, and moving it over and taking a look at it, it's going to oscillate. So a first order system does not oscillate, our second order system does oscillate, and we're going to see that the Bode plot actually indicates that it will in fact oscillate. The other thing I'd like to notice is note that this is a step response, a unit step in fact, and my amplitude is 1. So once again, the magnitude of the settling time there is, settling response is going to amplitude of 1. When I look at my Bode diagram, what I'm going to see is a magnitude of 0 at DC at 0 frequency. Let's take a look. So I'm going to make a new figure just so I don't lose that one. And I'm going to Bode plot system number 2. Okay, so this Bode diagram looks a lot different from the other one, which was, just flat and then attenuating. This one has this peak here. This peak is a resonant peak. It indicates to me, first of all, that my system is underdamped, that it will in fact oscillate. And even more, it'll tell me the frequency at which it oscillates by looking at where the peak is. So it's asking MATLAB once again to give me that data tip. And it turns out that frequency is give or take 3.16 radians per second. The phase is also very different from the original, so it was mainly flat until the resonant peak, and then we have a complete flip over. And so what this is going to tell us is that we need to be a little bit careful when we're looking at an input sine wave, because it might actually flip at 180 degrees, give or take. This one actually doesn't go exactly to 180 degrees, but it is very close. So let's now go back there. Let's do another LSIM for this system, and let's look at what happens when we give it a sine wave at this frequency, which is approximately 3.16. So I'm going to do that again. So my T, I'm going to keep as my lin space, 0, 10 in steps of 1,000. Now my U is sine of 3.16 times T. And again, what I'm going to do here is we're going to have an approximate frequency because everything is done numerically. So if we actually figured out the real resonant frequency, we might be able to figure that out, but we want to just look at the Bode plot. And now what I want to do is LSIM system 2 given the U and the T. And let's take a look at what happens. Oh, it's still giving me a step response. Sorry about that. Let us make MATLAB redo that. Okay, so take a look at what's going on here. Again, the gray is the input. It's just a regular sine wave. It's nothing special. And this blue here is the output. And notice how it's getting bigger and bigger and bigger. So this is exactly what resonance looks like. So if I have a resonant sine wave, my system is just going to continually get energy from that. Let's explore this though, because this system, what happens is we run time to even longer. So if I say my t is length space, let's say 10,000. Oh, my apologies. We want to actually run that for longer, so I want to do 1,000, but for 100 steps. And then my u is going to be the same. I have to recompute the u because I've recomputed the t. And then I'm going to LSIM again. And let's take a look at what ends up happening. So although that smaller LSIM up to 10 seconds made it look as though things were unstable, the Bode plot really gives us not much information regarding stability there. So we're not going to worry about the fact it looked like it was growing without bound. It in fact wasn't. We ended up with this maximum behavior here. So don't take that to mean that it was unstable, but this is definitely what resonance looks like. And again, the Bode diagram predicted that frequency at which it resonated was 3.16, and we see that in this response here, where a very small input sinusoid of only magnitude of 1 is in fact giving us a magnitude above 30 here, which is exactly what resonance looks like. So the Bode diagram, the one very important thing it can tell us for higher order systems is where and when it vibrates and resonates. So if I take a look at system number 2, and you'll notice that, if you recall things about second order systems, this is a spring constant, K. This is a damping coefficient, C, and this is like a mass, M. So we have mass of 1, damping coefficient of 0.1, and a spring constant of 10. What I want to do now is change into a new system and increase the damping coefficient and take a look at what the Bode plot gives me. So if I say now system number 3 is TF, and that was going to be 10, 1, and now let's give it a very large amount of damping, 10 and 10. And now we want to find the Bode diagram of system number 3. What you'll notice is that with a huge amount of damping, we do not in fact get a resonant peak. In fact, this one looks a lot like the first one we saw, that first order system, because when damping is big enough, a second order system essentially behaves like a first order system. All of its poles are on the real axis. So I never get this resonant peak here, and so I don't anymore have the concern that if I give it a sine wave, it's going to resonate. If I look at LSIM for this one, and I look only at system number 3, what you'll notice is precisely what we would expect. We have almost like first order like behavior. It looks very, very similar to that first order system we had. We have an input sinusoid, which is gray, and an output sinusoid, which has a magnitude strictly less than the input. So the Bode diagram was able to tell us where that happened. The final thing that you might find from a Bode diagram is called the phase margin and the gain margin. That was discussed in class, and there are notes on it. I don't want to replicate it here because MATLAB is really not the appropriate place to show the derivation of those things, but please note that the phase margin and gain margin can be read directly from the Bode diagram.